Hey everyone. So these notes are going to introduce a topic called congruency. Okay, so the word congruent or congruency is maybe a word some of you guys are familiar with. But how I kind of want you guys to think of it, congruence is almost like equality, right? But congruence is specifically going to relate to how two shapes are equal in size. Okay, but instead of using equal, we're going to use a more specific word called congruent. Okay, so at the top of our notes here says concept one. Use geometric descriptions of, we're going to fill in rigid motions. Okay, rigid motions. And we know rigid motions are just our isometric transformations, right? Those are reflections, rotations, and translations to transform figures and to predict the effect of a given rigid motion on a given figure. Okay, so rigid motions in the plane we know preserve the shape and size of the pre-image and image, right? So we know that it's going to be same shape, same size between our pre-image and image when given a rigid motion, whether it's a reflection, rotation, or translation. These motions are also known as isometric transformations. So far, this is all just review for us, right? We're already familiar with these terms and us discussing them from the previous week of class. Okay. It is no surprise that these two identical relationships leads us to congruence. In all ways, rigid motions, isometric transformations, and congruence speak to the same concept, which is the process of being identical. So process of being identical. Okay. So congruence of figures is defined by, so we're going to say two figures. So two figures meaning two shapes, right? Could be two triangles, two squares, two five-sided figures, okay? Two figures are congruent if and only if one can be mapped. So again, mapped is just another word for moved. Mapped or moved onto the other by one or more rigid motions. And again, those rigid motions, you're just thinking, oh, are isometric transformations, okay? Translations, reflections, and rotations are the rigid motions, and any sequence of these from one shape onto another would prove congruence. Dilations and other transformations that change the shape or size of the figure do not produce congruence. So do not produce congruence. Okay? Now this next section, it says a congruent statement relates one identical object to another by identifying the corresponding parts that match each other. So that word corresponding from here on out is a word we're going to be using a lot. Okay, so corresponding is kind of just like what matches up to what else, kind of in two figures. So for example, that's kind of a weird sentence I just said, right? If I'm comparing quadrilateral ABCD to quadrilateral MNOP, right? A quadrilateral is just a four-sided figure, okay? Let me actually draw these out for you. So let's say we have a quadrilateral here. We'll say it's A, B, C, D, and then I have quadrilateral here, M, N, O, P, and they're telling us that these two quadrilaterals are congruent. So you're going to see that symbol in between. It's going to have an equal sign, right? We know what an equal sign means. That just means equality, right, or same measurement. Okay, with the little squiggle above it, that's going to represent similarity in terms of the same shape. And didn't we just talk about two figures being congruent, where it's going to be same shape, same size? So same shape is going to represent the little squiggly in our congruent symbol, and then same size is going to represent the equal sign. And we put them together to form our symbol that represents congruence. Okay? So if I want to say, okay, if I know these two quadrilaterals are congruent, I know their corresponding sides and their corresponding angles are also congruent. So when I say corresponding, I know that point A in quadrilateral ABCD is going to correspond to point M in quadrilateral MNOP. That's because it's the first letter, right, of each quadrilateral there, okay? So it's kind of just a matching game right now. That means point B is going to correspond to point N. Point C would correspond to point O. And then point D is going to correspond to point P. Okay, and you can actually form congruency statements, right, by saying certain sides and certain angles are also congruent based on this information. So I can say, for example, side AB is going to be congruent to side MN. So I'm going to write that congruency statement off to the side. So now I'm going to write a line segment here, guys, and some of you might be familiar with this, okay? So if I want to say the line segment AB, I'm just going to put those two letters together next to each other and put a little line above them. That's going to indicate line segment AB. And I'm going to say is congruent to, right, that's my new congruency symbol, line segment MN. So MN with a little line above it. I can write statements for all the corresponding sides. So I can say that, okay, side NO is going to be congruent to side BC. I can say side PO is going to be congruent to side DC, and then side MP is going to be corresponding to side AD. Sorry, my paper got a little tilted there, okay? So we go ahead and just write those out too. So we already did the pink, A, B, and MN. Now I can do the green. So side BC is congruent to side NO. I can say side PO is congruent to side DC. And then I can say side, let's see, PM. I think I went backwards here, hold on. So let me be consistent in this. Since I was naming off the sides in the quadrilateral on the left-hand side first, so I said AB to MN, BC to NO. Let's just keep that congruency going. So I'm going to say side DC is congruent to side PO. So DC is congruent to side PO. Those are my blue sides here. And then side AD is congruent to side MP. Okay, those would be listing off my congruency statements to say, okay, the corresponding sides are congruent. Okay, I can also do the same thing with the angles, guys, quickly. So I can say like angle A, that 90-degree angle, right, is congruent to angle M, right, the corresponding angle. Angle B is congruent to angle N. Angle C is congruent to angle O, and then angle D is congruent to angle P. Now, how you guys represent angles is going to be that little inequality symbol. So I'm going to write them over here. So I can say angle A, right, the pink, is congruent to angle M, the pink. Okay, I can say angle B, the green, is congruent to angle N, the green. I can say angle C, underlined in the blue, is congruent to angle O, underlined in the blue. And then angle D, which is circled in the purple, is congruent to angle P, also circled in the purple. Okay, so a bunch of congruency statements that we can write here. Okay. Now, if these were named differently, so just continuing to read on here, for example, triangle, it should be a triangle. Triangle has 3 sides, but it should be quadrilateral ABCD is congruent to quadrilateral NPMO, then their corresponding congruent parts would be different. So it just matters the order of the letters, right? That's how you can match up corresponding points there. The order that they are placed in directly relates to corresponding parts. Again, kind of how I matched up the colors here, right? The first letter matches the first letter, second letter to second letter, third to third, and fourth to fourth. That's how you match up your corresponding sides and angles, okay? Now this key acronym here, so Cpcfc, try saying that 5 times fast, pretty hard, okay? So what we're gonna fill in here is gonna say corresponding parts of congruent figures are congruent. So that's Cpcfc. So all that means is that anytime you guys have 2 figures that are congruent, right, as identified by the symbol there, that means their corresponding parts are also congruent. That's all it means. Okay, kind of what you guys just did with identifying the parts up here. So that's what Cpcfc represents. Corresponding parts of congruent figures are in fact congruent. Okay. Now it's just showing you guys a quick couple examples here. We're actually not going to do any writing with this, just quickly identifying. So it's saying that these 2 quadrilaterals would be congruent because I can map my quadrilateral QRST to quadrilateral UVWX by a translation of 6 units to the left and 3 units down. So since I'm translating that shape and it would map my pre-image directly on top of my image, that means these 2 would have to be congruent, okay? Same thing here. So for my next figure, since I can take the pre-image, which is QRST, and I could technically rotate it 270 degrees, and it would map directly onto itself. Okay, that would prove that these two shapes are congruent. And then, man, some of this is incorrect. It should say a reflection over the y-axis. So I could take my figure ABCDE and reflect it over my y-axis to map onto JMWYH. And since it would lay directly on top of it, that would prove that these two figures are congruent. Okay. Now, if we quickly flip over to the back, okay, just a couple more examples like that. So these two top examples, right? This is showing you guys that technically sides can be congruent between two figures, but their angles also must be congruent in order to have them be equal, right? So we can see that we have a square here and looks like a rhombus here. Yes, their sides are matching, right? As identified by my little tick marks. So guys, these tick marks are just showing that all of these sides are the same length. Okay, and those same tick marks are also on your other figure here. Okay, but obviously those angles are different. Looks like we have like 90-degree angles inside my square here. And then these angles inside my rhombus, those are not the same measurement angles, so therefore they would not be congruent. Okay, and they show you the exact same example down below with a rectangle and a rhombus as well. Okay, same concept over here. They're giving you a square and a rectangle. Now they can have the same, oops, you can have the same angle, right? But if the side lengths are not the same, that means they're not going to be congruent, right? So a square and a rectangle would not be two congruent figures, okay? Same idea with these two equilateral triangles, right? Equilateral triangles just because all the angles are the same, right? But again, their side lengths, the corresponding side lengths are different in measurement. So again, these two would not be considered congruent, okay? Now, these last couple examples, guys, very similar to what we just saw down below here, just proving congruency, but it's just showing you more than one transformation taking place, okay? So it's just asking you, given two figures, use the definition of congruence in terms of rigid motions to decide if they're congruent. So my original relationship is going from triangle ABC to triangle RZY, and it's asking if these two are congruent, and they're showing you guys how if you take that triangle and you're to rotate it 90 degrees, and then take that triangle and flip it over the y-axis, it would result in that image triangle there, okay? So again, all you guys are trying to get out of this right now is, okay, miss, let me think. Two figures are only gonna be concurrent if I can map one onto the other, and when I say map, I mean move one onto the other by performing an isometric transformation, okay? Whether it's a rotation, reflection, or translation, okay? The bottom three examples show you guys some more. Okay, I'm not going to go through those just because of time, but you guys have those to refer back to in your notes.